Now let's consider the concept of mobility. What is mobility? The mobility is the magnitude of the drift velocity of a charge carrier per unit electric field. If we have, so mu denotes the mobility. If we have a drift velocity v, its absolute value for an electric field E, then mu is the mobility, absolute value of v over E. That gives us the mobility of the charge carrier. The mobility is defined to be positive, that is, it is directionless for carriers, both type of carriers, electrons and holes. The electric conductivity is the sum of the electron and hole contributions in the conductor. So, the conductivity sigma is given as the number density of electrons times the mobility of electrons plus the number density of holes times the mobility of holes multiplied by the charge. So, the mobility of electrons can be given as charge times the mean free time, that is the relaxation time, over the effective mass of electrons, and that for hole, mobility for hole can be given as charge times the relaxation time for hole over the effective mass of hole. These taus are the relaxation times. Now, if we have impurity in the semiconductor, then we have a completely different kind of a picture. If we consider silicon, silicon has 4 coordinations. It's a 3-dimensional structure. If we have one silicon atom here, then it is coordinated with one atom here, one atom here, one atom here, and one atom on this, out of this plane, somewhere say here. Could not draw it properly. Let's shift it a bit like this. So, all these are silicon atoms. This is the kind of arrangement silicon forms, and you can see that silicon at its outermost shell has 4 electrons. Now, if we replace one of these silicon atoms with, say, a phosphorus atom, in place of silicon we put a phosphorus which has 5 electrons in the outermost shell. So, it contributes one more electron into the system. It's a donor kind of an impurity, and this donor adds electrons to the system. So, it dopes N type. In contrast, if we add a boron here, if we replace this silicon with a boron here, then what happens? Boron has 3 electrons at the outermost shell, therefore it adds a hole to the system. So, the doped carrier, nature of the doped carrier becomes hole like p type, and it is an acceptor. That is the kind of system it becomes, and those are the carriers, and they govern the transport in the system. And you have already learnt how they form the active elements in a semiconductor device. and a device circuit like diodes, transistors and all. Now let's see the Fermi surface, the band structure in reduced zone scheme and all that. What is a reduced zone scheme? We have drawn the band structure in the context of nearly free electron model. We are going to do something similar here. Let's consider this to be the first Brillouin zone. This is the second Brillouin zone. This is the third Brillouin zone, and so on. If that is the situation, then in nearly free electron model we have seen that the bands look somewhat like this. And so on. So this part is called the extended zone scheme. And if we now plot everything within the first Brillouin zone, that would be reduced zone scheme. That means we would have this one translated here and this one translated here. We will have a band looking like this. Sorry for my drawing, but this is the idea. This one is called a reduced zone scheme. And if we repeat this reduced zone scheme on each zone, that would be called a periodic zone scheme. We are not plotting that periodic zone scheme here, but that's the idea of getting a periodic zone scheme. Mostly we plot band structure using this reduced zone scheme. Now let's consider the idea of Fermi surface. Let's consider a two-dimensional Brillouin zone because that is something we can show. The boundary equation of the zone boundary can be given as twice k dot g plus g squared equals 0. It is satisfied if k terminates on the plane normal to the g vector and at the midpoint of g. So the first Brillouin zone of a square lattice is the area enclosed by the perpendicular bisectors of G1 and the 3 reciprocal lattice vectors equivalent by symmetry. So the first, if we have reciprocal lattice points somewhat like this, then these are the bisector planes. This becomes the first Brillouin zone. Then comes the second neighbor, that's here. So these are the bisector planes. This gives us the second Brillouin zone here, here, here and here. Similarly, we can obtain the third Brillouin zone by drawing another extension of this, and the Fermi surface, it won't be a surface if we consider a two-dimensional Brillouin zone. It would be surface only in the context of three-dimensional Brillouin zone. Here it would be a contour, and if we consider free electron-like systems, then we will have a circular shape of that Fermi contour. So something like this, for example. Let me draw it in a different color, and let me try to draw it a bit more consistently so that the picture is a good one. So it would look somewhat like this. This would be the Fermi contour. Its extension for three-dimensional Brillouin zone or three-dimensional reciprocal lattice, three-dimensional real lattice is the Fermi surface. So what we have drawn here is not confined within the first Brillouin zone, and using this kind of a reduced zone scheme that we have discussed here, we can bring it into the first Brillouin zone by translating different parts of it into different sections of the first Brillouin zone. It won't look like a circle anymore, but that's the circular Fermi contour in essence.